Okay, here we got the final lesson for chapter 1. This is 1.6, and it comes back to a connection of a concept that we had earlier on in this year, which was dealing with horizontal asymptotes. So here's what we got on this. So the limit as x approaches negative infinity or positive infinity is always approaching a horizontal asymptote. So if you are forever heading to the left or forever heading to the right, the limit, if you have a limit, must be heading towards a horizontal asymptote. Otherwise, if it was going forever up or forever down, it would be approaching a positive infinity or negative infinity. But if it's approaching a real value, then that value that it's approaching must be a horizontal asymptote. So if r is a rational number, and c is an element of the real number system, in other words, c is basically like a constant that we have up there. So the limit as x approaches infinity would be 0 in a case like this where you have a constant on top and your x is on bottom. As x approaches infinity, that basically means your denominator is getting bigger and bigger and bigger and bigger. So overall, this fraction would be reaching a value that is smaller and smaller and smaller and smaller, so closer and closer to 0. So whenever you're doing ones like these, one thing that has always helped me in the past is just plug in some real numbers. If you're ever kind of unsure as to what this would be, or you forget the rule, just plug in some real numbers, and I think that's a good way of looking at it. So let's just say my c value was 5, and my denominator is getting larger and larger and larger. So let's just say x was 10. So it could be 10 to the first. It could be 10 squared. It could be, I'm just going to keep going for a few of these so you can see it here. But so you can see what would happen. If I keep putting zeros here, I'm going to get closer and closer and closer to 0 the bigger my exponent gets on my 10. The same thing happens with negative infinity. This would all be the same information, but they would just be negative instead of positive, because I would be putting in negative numbers for x instead of positive. So I still get the same layout of numbers, but they would just be negative. So it's still approaching 0. It's just approaching it from the left instead of from the right. All right, but in both cases, you'd be approaching 0 for ones like this. So this takes us back to what we learned a long time ago, pretty early on first semester, when we were doing horizontal asymptotes, where if the denominator had a bigger exponent than the numerator, we said that the horizontal asymptote was y equals 0. Right? So that's why the limit is also 0, because it is approaching the horizontal asymptote as x approaches infinity. So we'll kind of make that same connection down here. Side note, if you were to have infinity over infinity, we have a case that's called indeterminate, and you'll see something like that right here. So this hints is what I'm talking about with what we've learned earlier this year as far as some rules of horizontal asymptotes. So I'll get to that in just a second. Take a look at this case. So here's a case where x is approaching infinity, but I have an x to the first on top and x to the first on bottom. So they have the same exponent. So if you really wanted to solve this sort of with an algebraic approach and really be able to do this by hand, the way that you do this is you simply divide all of your terms by x to the first. So whatever your exponent is, in this case it's x to the first, if you divide everything by that, you can simplify it to a point where you can see what your horizontal asymptote is or what your limit is. So same thing in these cases. So I took all 4 of these terms, divided them all by x. So that's what you're seeing right here. So remember what we learned on this little guy, that when your denominator has a bigger exponent than your numerator, right, that the limit of this term specifically is approaching 0, as well as this one. So these guys essentially 0 out, and I'm left with just this guy over this guy. I'm going to let my x's cancel, so it becomes just 4 over 2. So if you simplify that, you get 2. So that's an approach that is like the algebraic approach and totally works. Let me show you the rules on this. And again, this goes right back to something we learned earlier this year. If the exponent on top is smaller than the exponent on bottom, then your horizontal asymptote is 0, which also means your limit is 0. If they are the same, and you might remember this one, when the numerator equals the degree of the denominator, so if it's like x to the first over x to the first, like we had right here, the rule was the horizontal asymptote is just this coefficient divided by this coefficient. So 4 over 2. And that gets you this guy as well. If the numerator has a bigger exponent than the denominator, then there is no horizontal asymptote, so we would need to say that it does not exist. Because again, if in order to have a limit, it needs to be approaching a horizontal asymptote if you're heading forever to the right or forever to the left, right? It needs to be approaching a horizontal asymptote. So, and that's basically what I was just describing right there. Those were just notes to myself, but that's what I was saying. Let me give you some real examples to go with these guys. So here's a case where exponent on bottom is bigger than the one on top. So because of that, again, the rule says the horizontal asymptote is y equals 0. So as you head forever to the right, you would be forever approaching y equals 0 in a graph like this. And you could certainly, if you want to always check these, put that into a calculator and graph it. Take a look at the graph, and as you head forever to the right, you'll see that the graph is getting closer and closer and closer to 0. If they are the same, x to the first over x to the first, then again, we just divide the leading coefficients, and it just becomes 3 over 2. The steps that you're seeing here are basically the algebraic approach. So again, because my biggest exponent is x, I am just dividing every single term by x in order to accomplish the same answer, right? So these guys would end up just canceling out, so I end up with just 3 on top. This one cancels out, so I end up with just 2 for that term. With the 5 over x, the limit of that term would be approaching 0. And so he becomes a 0. And so I'm left with just the 3 over 2. So this is the process, and you may be asked to show this process. So again, the rule of thumb is, and this is what's going on in all 3 of these, you're simply dividing every term by whatever has the largest exponent. So all 4 of those terms got divided by x squared, which is what you're seeing in the second step. And if you clean that up, you're leading into this answer right here. The last one here, again, you could take the algebraic approach. I could divide every term by x squared, which should look like this. So this one was not set up correctly. Everything should have gotten divided by x squared. And I'll show you why, that this becomes a does not exist. It should not become infinity. So that guy is not correct. So as you look at these guys, these x squares would cancel. And so I would just have my 3 on top. For these guys, and this is where sort of the key is, so why you can see it does not exist. Remember that if the bottom exponent is bigger than the top exponent, then the limit of that specific term is approaching 0. So that would become 0, and that would become 0. So you end up with a 0 denominator, and that's why it's undefined. And that's why we would say that the limit does not exist for cases where your exponent on top is bigger than the one on bottom. All right. Final page. All right, last couple examples here. So just kind of a trick that you can take on cases like this where you're dealing with a square root or any kind of a root. Keep in mind that the square root of x squared is still x. So because of this guy, I want to divide all 3 terms by x. So I'm dividing the top by x, and I'm dividing the bottom by x, essentially, right? Since the square root of x squared is still x. So that allows me to rewrite it with this look right here. So if we just start simplifying things, we know this guy would just equal 1. So let me bring it down to this. Here's that case where if your exponent on bottom is bigger than the exponent on top, then you get a 0 for the limit on that guy. So it becomes just 1 over the square root of 1, which would simply be 1. Do keep in mind that as long as your x's are positive, so as long as I'm approaching positive infinity, then this equation is true. But if you were approaching negative infinity, so if x was a negative number, then the square root of x squared would actually equal negative x. And so I tried to throw in a real number here for you just so that would make more sense. But let's just say that x is negative 10. Right, so I sub that in for x. So if you were to square this, it would become positive. So then when you square rooted it, you'd be left with a positive 10. Well, that wouldn't equal negative 10. So you got to throw the negative in order to adjust the sign, right? And so now you would have positive 10 equaling positive 10 to make it a true statement. So if x is approaching negative infinity, then just remember that this statement would equal negative x instead of positive x. So look at this guy. So if this was the same scenario, but now x is approaching negative infinity, again, I'm going to divide everything by x. So we're dividing the top by x. I am dividing the bottom by x, right? Based on what we just talked about up there. And so now because these are both under square roots, we can write that as one big square root, just like we did up above. And then it cleans up the same way. It just becomes a negative instead of a positive. So, and then all that was based on this being negative infinity instead of approaching positive infinity. And then the last thing we got to take a look at here is the limit as x approaches infinity. I wanted you to see this one because I didn't want you to confuse the limit of sine of x over x that you've seen before, simply because the one that you saw before, and this is what you got to be really careful on, is the one that we saw with sine x over x before was when x is approaching 0, right? And that's when you had a value of 1 for that guy right there. So again, that was when x is approaching 0. But if x is approaching infinity, right, like it is in a case like this, then our limit becomes 0 instead of 1. And so it's just those little things that we would have to pay attention to, like this, like what are we approaching, in order for either one of those to be true. And again, one kind of fallback method that I really enjoy is just take a look at the graph. If I were to graph the sine of x over x, let me just throw it in real quick so I can point something out. So if I did, let's see, sine x over x. I don't know how pretty this will be because I haven't adjusted my window yet, but let me just graph it real quick and then we'll take a look at it. Good enough. So right here is what I'm getting when I approach 0, right? So this is where, as I approach 0 from either side, you can see that I'm getting a y value of 1. But if I am approaching infinity, so you'll notice this graph starts heading off forever to the right, and as it goes, it's getting the amplitude shrinks as you go. So it gets a little more and more shallow as you head off towards infinity, which is why you are now approaching a limit of 0 when x is approaching infinity, right? And so that's the difference between this guy and this guy, right? So just make sure we're looking for what are we really approaching, because that definitely affects the limit that we're taking a look at. So, but that's it. That's the end of chapter 1.